Good morning. Here I'll solve a problem illustrating axial flow turbine. The statement of the problem is, in a zero reaction gas turbine, that is in an impulse turbine, the blade speed at the mean diameter is 290 meters per second. Gas leaves the nozzle ring at an angle of 65 degrees to the axial direction, while the stage stagnation temperature is 1100 Kelvin. The following pressure were measured at various locations. At the nozzle entry, the stagnation pressure is 400 kilopascal. At the nozzle exit, the stagnation pressure 390 kilopascal. At the nozzle exit, the static pressure is 200 kilopascal. At the rotor exit, the static pressure is 188 kilopascals. Assume that the magnitude and the direction of velocities at entry and exit of the stage are the same. Determine the stage total to static and total to total efficiency. The following constants should be used. The specific heat of turbine gas at constant pressure Cp can be taken as 1148 joule per kg K. The ratio of specific heat gamma is 1.33, and the gas constant R can be taken as 287 joule per kg per K. I have solved the problem here. I have given a schematic of an impulse stage where the nozzle followed by the rotor have been indicated. Let me take Z be the axial direction and theta be the tangential direction. The gas condition or the gas state at inlet to the nozzle is indicated by 1, exit to the nozzle is indicated by 2, and exit to the stage is denoted by 3. The C2 be the exit velocity of gas from the nozzle that makes an angle alpha 2 with the z-axis. Similarly, relative velocity at inlet to the rotor is W2 and exit from the rotor is W3. So W2 makes an angle beta 2 with the z-axis and W3 makes an angle beta 3 with the z-axis. For an impulse turbine, we know there is no enthalpy drop, static enthalpy drop in the rotor. So H2 must be equal to H3, and thus T2 is equal to T3. W2 and W3, they are equal in magnitude but opposite in sign. And similarly, beta 2 and beta 3. So beta 2 and beta 3, they are equal in magnitude and opposite in sign. With this, let me draw the velocity triangle. So U is the blade speed, W2 be the relative velocity. So U and W2 is equal to C2. So this is W2, this is U, and this is C2. Let me take another color. So this is W2 and W3, they are almost equal in magnitude. So this is W3 and this is C3. So thereby W2 makes an angle beta 2 with the z-axis. C2 makes an angle alpha 2. Similarly, W3 makes an angle beta 2 and C3 makes an angle alpha 3. So this will be beta 3. So this is so far the velocity triangle, and it has been given that axial velocity Cz throughout the stage remains constant. Okay. And also I can say W theta 2 must be equal to W theta 3, but they are in opposite signs. So I can write by magnitude they are equal. That is, peripheral velocity of W2 and W3, they would be also equal, as W2 and W3 are equal in magnitude. Now what are the quantities are given? Blade speed is given as 290 meter per second. Alpha 2 is given as 65 degree. T01 is given as 1100 Kelvin. P01 also given 400 kilopascals. P02 390 kilopascals. P2 200 kilopascals. P3 has 188 kilopascals. We'll have to evaluate eta total to static and eta total to total. By definition, this is the quantity which are given. Now by definition, eta total to static is T01 minus T03 divided by T01 minus T3s. That means with respect to this static condition at exit. And eta total to total is equal to T01 minus T03 divided by T01 minus T03s. That is, with respect to, it is defined with respect to isentropic condition at exit. For the nozzle, I can write total temperature at inlet must be equal to total temperature at exit. Now hence I can use isentropic relation to calculate static temperature at exit. Thus T2, I can write T02 into P2 divided by P02 to the power gamma minus 1 by gamma. Now T02 equal to T01, so put the values. So this would be equal to 1100 1100 K. P2 static pressure, this would be P2. P2 would be equal to 200. P02 is given as 390 kilopascals. And if you consider gamma as 1.33 minus 1 by 1.33, it will be 0.25. If you consider gamma is equal to given as 1.333, right? So if considering gamma is equal to 1.333, value of gamma minus 1 by gamma would be equal to 0.25. Now if you evaluate, if you calculate this, T2 would come as 931 Kelvin. So I have got the value of T2, that is exit temperature of the nozzle. Now I can write T02 total temperature at the exit of the nozzle minus T2, that is static temperature, is nothing but C2 squared divided by twice Cp. From this relation, I can write C2, no need to give this square, you can write square root twice Cp into T02 minus T2, right? We know the value of T2, T02 and T2. So this would be equal to root over twice, value of Cp is 1148, T02 is equal to T01, so 1100 Kelvin. T2 I have calculated as 931 Kelvin. If you calculate this, I have got C2 as 622.9 meter per second. So what I did, I have evaluated T2 and then I have calculated C2. C2 is the exit velocity of gas from the nozzle. Now from velocity triangle, I can write Cz, considering axial velocity remains constant within the stage. I can write Cz is equal to C2 into cos alpha 2. C2 is equal to 622.9 cos alpha to cos of 65 degree. If you evaluate, you will get 263 0.25 meter per second. Please check the calculations. Now after this, I can write again from velocity triangle c theta 2, that is tangential component of C2 is equal to C2 into sine alpha 2. That should be equal to 622.9 into sine 65 degree. If you do the calculation, we'll get 564.5 meter per second. And I can evaluate W theta 2 from velocity triangle equal to c theta 2 minus u. C theta 2 I have evaluated as 564.5 and u is as given as 290 meter per second. So if you evaluate this, this should be 274.5 meter per second. So I have got W theta 2 now. I have got C theta 2 and I have got W theta 2. So I am solving inlet to the rotor. For a zero reaction machines, that is for an impulse turbine, I can say W theta 3 in magnitude they are equal, but they are opposite in sign. So hence I can say C theta 3 from velocity triangle is equal to U minus W theta 3, that is equal to 290. What is the value of W theta 3? That is 274.5. And after evaluating, I have got 15.5 meter per second. Please note that C theta 3 is positive. Again, I am telling, please note that C theta 3 is positive. This means C theta 3 is in the direction of U. Please note that C theta 3 is positive, which means C theta 3 is in the direction of U. That is rotor rotations. Now I can write again from velocity triangle C3 squared. C3 is the exit velocity of gas from the rotor is equal to Cz squared, that is axial velocity, plus C theta 3 squared. Now I know the value of Cz and C theta 3. So if I put those values, 63.25 CZ, that square, plus 15.5 square. And after evaluating, I got 69540 meter square per second square. Now I have got CT squared, so I can write total temperature at the exit of the blade rotor T03 is equal to T3 static temperature plus C3 square divided by twice Cp. Now T3 is equal to T2, right? So this is same as T2, being an impulse turbine. So T2 I know, so value of T2 is 931. I've evaluated earlier. Now C3 square I have just calculated, which is 69540 divided by twice Cp. If you do these things, you will get T03 as 961.29 Kelvin. So here I have evaluated total temperature at exit of the stage. Now let me go to the next page. Now using isentropic relation, I can write Tcs, which is static temperature at the exit of the stage, divided by T01 is equal to P3 divided by P01 to the power gamma minus 1 by gamma, or I can write static temperature at the exit of the stage T3s is equal to T01 into, this will be P3, P3 divided by P01 to the power gamma minus 1 by gamma. Let us put all the values. 1100 Kelvin, P3 I know 188, P01 I know as 400, divided by 0.25. And if you evaluate this, you will get 910.8 Kelvin. Thus now I have evaluated static temperature at the exit of the stage. So I can define total to static efficiency eta Ts as T01 minus T03 divided by T01 minus T3s. Now I know all the values, put all the values, that is 1000, T01 is 1100 Kelvin minus T03 Just I have evaluated which that is equal to 961.29 divided by 1100 minus T3S I have calculated as 910.8. After calculation, I got eta TS, that's total to static efficiency, as 0.733, that is 73.3%. So I have evaluated total to static efficiency as 73.3%. Now let me define total to total efficiency. Now we know eta TT as T01 minus T03, total temperature in the stage, divided by T01 minus T03S. So actual temperature drop divided by isentropic temperature drop, total temperature drop in the stage. Now here, let me make an assumption as T03S minus T3S, please refer to HS diagram, is approximately equal to T03 minus T3. Now I know the value of T03 and I know the value of T3 also. Now this is equal to 30.29 Kelvin. T03 was 961.29 and T3 was 931. T3 is equal to T2. Here one should note that for an impulse turbine, T3 must be equal to T2 because there is no change of temperature or static enthalpy. From here, I can evaluate T03S as I know the value of T3S. So T03S is equal to 30.29 plus 910.8. So this is value is 941.09 Kelvin. So I have evaluated T03S. Now from this equation, eta TT, I can write eta TT total to total efficiency as 1100, that is T01. T03 is 961.29 divided by 1100 minus 941.09. If you do the calculation, you will get this is equal to 0.733 873. So total efficiency I have evaluated now, which is around 87.3%. Thus, one can see eta total to total is greater than eta total to static. I have solved an illustrative example for gas turbine and evaluated eta total to total and eta total to static. And through this example, I have also indicated that eta total to total is higher than eta total to static. Thank you for listening.